Good evening, dear students. Yes. So, in the last class, we were discussing about the chapter aldehyde, ketones, and carboxylic acid. Right. So, what we were discussing there. So, we were discussing the last part which we have discussed is about the nucleophilic substitution reaction. Right. We have discussed about the nucleophilic substitution, the mechanism. We have seen about the Yes, so chemical reactions we were seeing. Okay, so the mechanism of nucleophilic addition reaction. Okay, so how the addition nucleophile, okay, how it attacks the carbonyl carbon and how the addition takes place. So these things we have discussed. We have discussed about the reactivity. Okay, then we have seen some of the important examples of nucleophilic addition. Okay, that is first one was addition of hydrogen cyanide. Okay, across the carbonyl carbon, which yields you a cyanohydrin. Okay. Then we have discussed about the addition of sodium, sodium hydrogen sulfide. Okay. So here the sulfide group, okay, it attacks the carbonyl carbon, and what you get a hydrogen sulfide addition compound. Then we have seen the addition of alcohols. Okay, so we are adding alcohol. So 1 mole of alcohol, when you add, you will get a hemiacetal. So 1 more molecule of alcohol, when it reacts, okay, you are going to get a hemiacetal. Okay, acetals. Okay, so hemiacetal, okay, only one, and acetals means you are going to get both. Okay, you can see both the hydrogens will be they are replaced by your alkyl group. So you are going to get a gem dialkoxy compound. Okay, which are commonly called as the acetals. Okay, then we have seen the addition, okay, of the ethylene glycol. Okay, so ketone is reacting with ethylene glycol, and you are going to get a ethylene glycol ketal. Okay, so then we have seen the addition of ammonia and the derivatives. Okay, you are going to get different systems. That is imine system. Okay, so this is the imine system, that is C double bond NH. It is a imine system. Then so here you can see, first I have taken ammonia. So with ammonia, I'm going to get a imine system. If I react the carbonyl carbon with your primary amine, you're going to get a substituted imine, that is called as a Skips base. Then when I react it with a hydroxyl amine, okay, I'm going to get what? I'm going to get a oxime. Okay, so please see the double bond placement. Okay, C double bond NOH. Okay, so here, so to N where it is attached. Okay, so that is important. So based on that, the products are formed. Then here, the carbonyl carbon, okay, reacting with the hydrazine, you're going to get a hydrazone. Okay, and then carbonyl carbon reacting with phenyl hydrazine to give you a phenyl hydrazone. So these things already we have discussed in our last class. Okay, so let us go further. So let us start our today's class. Okay, so we are going to start. So here we are going to start with the reduction. So reduction of alcohol. So I hope what you know what is the meaning of reduction. Reduction is nothing but removal of oxygen or addition of hydrogen. Okay. So what we are doing here, we are reducing we are taking ketones or aldehydes and we are reducing it to respective alcohols. Okay. We are using some good reducing agents. Okay. So I hope you know some of the good reducing agents. So here is a list of okay, so here is lithium aluminum hydride, which is a strong reducing agent. Okay, and we have also used a sodium borohydrate. So these are the two reducing agent. So amongst this, your lithium aluminum hydride is a strong reducing agent, and your sodium borohydrate is a weak reducing agent. Okay, so THF. Okay, so tetrahydrofuran or ether is used as a solvent here. Here also tetrahydrofuran or ether is used as a solvent. So all the reagents or all the reducing agents, or okay. So whenever you are using any agent, we are using it along with some solvents. Okay. So aldehydes, ketone, carboxylic acid, acid chlorides, nitriles, esters, nitro compounds. Okay. So we are using here, okay, to reduce these compounds, we are using the lithium aluminum hydride. And where sodium borohydride is used for aldehyde ketones and acid chloride. So whenever you want to reduce acid chlorides, ketones, okay, aldehyde, so they are reduced by sodium borohydride. So what happens when you use lithium aluminum hydride? Your conjugate double bond gets reduced. Okay, the conjugate double bond gets reduced, and in sodium borohydride, conjugate double bond does not get reduced. Okay, then lithium aluminum hydride isolated double bond does not get reduced. In with respect to sodium borohydride, when we make use of that, your isolated double bond does not get reduced. Okay, so these are the significance, or you can say these are the differences, okay, based on which we are using the reducing agent. Okay, the role is same. Both are reducing agent, but one is a strong reducing agent, other is a weak reducing agent. So let us see. So we are taking a respective aldehyde. We are making use of lithium aluminum hydride, which this we have taken. We are taking the your ether. Okay, what we have taken here? We have taken the ether, or you can use tetrahydrofuran. So what, when you are taking aldehydes, so aldehydes are reduced to alcohol. They are reduced to primary alcohol. Okay, so hydrogens are added. Okay, hydrogen is added here across the double bond. So I'm going to get RCH2OH. So primary alcohol. Similarly, when I take ketones, so either of this you can use. Okay, then in the presence of sodium borohydride, I'm going to get what? You are going to get what? You are going to get a secondary alcohol. Okay, so aldehydes, they are reduced to primary alcohol. Ketones are reduced to secondary alcohol. Yes? Okay. So next is reduction to hydrocarbons. So the carbonyl group of aldehydes and ketones is reduced to CH2 group. Okay. There are two important name reaction, very important name reaction. Please mark this as very important. Okay. The first one is the Clemenson's reduction. Okay. First one is the Clemenson's reduction. Second one is the Wolff-Kishner reduction. Okay, both these reductions, or both these reactions are the reduction reactions. Okay, okay, and what we are doing, we are converting the respective aldehyde or the ketone to hydrocarbon. Okay, so let us see. Well, let us see. So first one, the Clemenson's reduction. Carbonyl group is reduced to CH2 group. How we are reducing it to CH2 group? We are making use of zinc amalgam. We are making use of zinc amalgam. Okay, that is ZnHg. Okay, and in the presence of concentrated HCl, in the presence of concentrated HCl, so what is happening? Your carbonyl carbon, okay, your carbonyl carbon is it has been reduced to what? It is reduced to your CH2, that is your hydrocarbon. Okay, very important. So please mark this important. Clemenson's reduction. What we are doing in Clemenson's reduction, students? Carbonyl group is reduced to CH2 group when we are treating it with zinc amalgam and concentrated hydrochloric acid. Okay. Then the next one is Wolff-Kishner reduction. Okay. So what we are doing here, which is the agent here? We are making use of hydrazine. Okay. We are making use of what? We are making use of hydrazine. NH2 is called as hydrazine. So again, we are taking, either we can take a aldehyde or a ketone. Okay. And we are treating it with hydrazine. Okay. Followed, we are going to heat it. Okay. We are going to heat it with potassium, sodium hydroxide, or you can use the potassium hydroxide, in which solvent we are going to use a ethylene glycol solvent. Okay, the solvent uses ethylene glycol. We are going to get a hydrocarbon. Okay, we are going to get a hydrocarbon. Understood? So what we are doing at Wolff-Kishner reduction, we are taking We are converting the aldehyde or ketones. Okay, we can take either of this aldehydes and ketones. We have to treat it with hydrazine. Okay, when you treat it with hydrazine, okay, I'm going to get what here? What is this? NH2. Yes, I'm going to get a hydrazone. So the intermediate form is a hydrazone. This hydrazone, I'm going to heat it with potassium hydroxide in the presence of ethylene glycol as a solvent. I'm going to get a hydrocarbon. I'm going to get a hydrocarbon. Okay. Again, one more reaction. What we can make use of? We can make use of carbonyl carbon. Okay. Heat it in the with red phosphorus at 420 Kelvin. I'm going to get a hydrocarbon. Okay, so let us see example. So let me take any aldehyde and a ketone. So for Clemenson's reduction, okay, let me take this as acetaldehyde. Okay, so acetaldehyde is CH3CH double bond O. Okay, in the presence of zinc amalgam and concentrated HCl, what I am going to get? I am going to get a what? I am going to get what here? CH3. Okay, so I'm going to get here CH3 and CH3 plus H2O. Okay, CH3, CH3 plus H2O. So this is the product which is formed. So this is the what? Ethane. Okay, this is the ethane. I'm going to get what? I'm going to get a hydrocarbon. I'm going to get a hydrocarbon. Okay, so CH3, CH3. Okay, so hydrogen reduction is what? Addition of hydrogen. So we are adding hydrogen. Okay, CH3, CH3. Okay, fine. Then next, Wolff-Kishner reduction. So let me take this as benzaldehyde. Okay, let me take as a benzaldehyde. So this is a benzaldehyde. Uh, double bond O H. So benzaldehyde in the present with the your hydrazine NH2 NH2. Okay, you are going to heat it in the presence of your this first. What will be there? First will be a hydrogen formation. So let us write the hydrogen formation. So H double bond N NH2. Okay, hydrogen formation. Then react it with your potassium hydroxide in the presence of ethylene glycol. Okay, here presence of ethylene glycol. What I'm going to get? I am going to get a toluene CH3. Okay, I am going to get a toluene. So this is, or you can call it as methyl benzene. The name is methyl benzene. Understood? So these are the name reactions. So namely the Wolff-Kishner reduction or and the Clemenson's reduction. Is it clear? Yes. Okay. So let us go for the next one. So I hope Clemenson's reduction and Wolff-Kishner you have understood, very, very important. Okay, next we are going to see oxidation. Okay, next we are going to see okay, so next is oxidation. What do you mean by oxidation, students? What do you mean by oxidation? Oxidation is what? Addition of oxygen or removal of hydrogen. Okay, addition of oxygen or removal of hydrogen. So aldehydes and ketones, okay, aldehydes, they differ from ketones in their oxidation reaction. Okay, how they differ? The aldehydes, how they differ from the ketones in their oxidation reaction. Okay, so aldehydes and ketones. So aldehydes, they can be easily oxidized. Okay, aldehydes, when you do oxidation, it can be easily oxidized to what? It can be easily oxidized to your this what carboxylic acids. Okay, so which are the good oxidizing agents? So the in oxidizing agent, again there are strong oxidizing agent and there are weak oxidizing agent. So strong oxidizing agent are nitric acid, potassium permanganate, and potassium dichromate. And which is a weak oxidizing or mild oxidizing agent? The mild oxidizing agents are like Tolman's reagent and Felling's solution. Okay, so where does oxidation occurs? It occurs mainly at room temperature, and the cleavage of CC bond does not take place. Okay, during the aldehyde, that is during the oxidation of aldehyde, only one carboxylic acid gets formed. Okay, so aldehydes are easily oxidized to carboxylic acids. Okay, in the presence of oxidizing agent, they are converted to carboxylic acid. Okay, and what about ketones now? What about ketones? What about ketones? So ketones cannot be oxidized easily. Okay. So it cannot be oxidized easily and vigorous oxidation is required. Okay. Vigorous oxidation is required when we are using the oxidation for the ketones. Okay. So it cannot be easily oxidized. Only strong oxidizing agents can be used. So when you are using oxidizing agent for aldehyde, you can use either strong or mild. But when you are oxidizing ketone, you have to only use strong oxidizing agent. So here the oxidation occurs at high temperature. Okay. Then the cleavage of CC bond takes place. And here the mixture of carboxylic acids are formed. Okay. Here the mixture of carboxylic acids are formed. Okay. Yes. So these are the reactions. Okay. So here you can see I have taken aldehyde. I am using a strong oxidizing agent. I can take KMnO4. I can take potassium digromate. So what is happening? I am going to get a carboxylic acid. Similarly, one example. Okay, with example we will see. So I have taken here CH3, CH2, CHO. Okay, propanaldehyde. So what I am doing, I am using a oxidizing agent. So I am going to get a propanoic acid. Okay. Then again, ketones. I have taken a ketones here. So what I'm going to do with ketones? So ketones I am going to, so you can see, okay, so this is one group. This is another. Okay. So I'm going to do oxidation. Okay. So what I'm going to get? So the cleavage will take place at one, this, okay, CC bond. So here the CC bond cleavage takes place. So what happens? CHC, COOH, one product, another is CH3, CH2, CH2, COOH. Okay, so addition of oxygen takes place. So again, okay, so another example. So these are the different examples. Okay, so like this, we are going to get the oxidation. So remember the rules. So when we can use oxidize when we are oxidizing the aldehydes, it can be oxidized by using both strong as well as mild oxidizing agent. And when we are using oxidizing the ketones, we can only use the strong oxidizing agent. Okay. So here, let us see the distinguishing test, okay, between the aldehydes and ketones. So which are the different distinguishing tests which can be used? So first one is the tolerance test. Okay, tolerance test. So what do you mean by tolerance test? It is also called as the silver mirror test. Mark this as very, very important. Mark this as very, very important, student. So this is also called as what? Silver mirror test. Okay, silver mirror test. Silver mirror test. Okay, so what we are doing here, what is present in tolerance reagent? It is the ammonical, okay, ammonical solution of silver nitrate. Okay, ammonical solution of silver nitrate. Okay, so what we are doing, we are taking aldehydes, okay, and we are heating it with tolerance reagent. So what it forms? It forms a bright silver mirror. Okay, bright silver mirror, which tells you the formation of a silver metal. Okay, it tells you the formation of a silver metal. So what is happening during this reaction? The aldehydes, they are getting oxidized to corresponding carboxylate ion. So the aldehyde is getting oxidized to corresponding carboxylate ion. Is it clear? Okay. So here, so what we are doing here, so tolerance reagent, very, very important, as I have said. Okay, tolerance reagent. So it is also called as a silver mirror test. Okay, what is the solution? It is a ammonical silver nitrate solution. So when we take aldehydes, when we heat it with Tollens reagent, they get oxidized to carboxylate ion. Okay, and it gives you a bright silver metal. Okay, yes. So what is the formula? If they ask you, so this is the formula of Tollens reagent. Okay. You can see here the test tube, right? You can see the test tube here in the right side. Yes. So you can see how it is silver color, like a silver mirror. Yes. So this test is only answered by the aldehydes. Okay. And ketones, they will not show this positive test. Only who will show the test? Only the aldehydes will show this test. Okay. So what is the formula for Tollens reagent? It is this. Okay. So I have written here. So here both type of aldehydes, they will give you the this what test. Okay, both aliphatic as well as aromatic aldehydes will show the Tollens test. Okay, so Tollens test is very important. So where it is used? It is used for testing the aldehydes. Okay, what is the formation? It gives you a silver mirror formation. Okay, silver mirror formation is given. Okay. Let us go for the next one. Next is Felling's test. Next is what? Felling's test. Okay. So Felling's test, it consists of mainly two solutions. First one is Felling's A. Another is Felling's B. What does Felling's, how it is formed is, it is a good oxidizing agent. Okay. How we are going to get the Felling solution is by mixing two solutions, Felling's A and Felling's B. Felling's A, it consists of your aqueous copper sulfate. Okay, it consists of aqueous copper sulfate, and your Fellings B, it consists of the sodium potassium tartarate, that is called as the Rochelle salt. Okay, and both are taken in a equal amount. Okay, both these solutions, they are taken in equal amount. Okay. Now what we are going to do? We are going to take the aldehyde. So what is the test? We are going to take the aldehyde. Okay, we are going to react it with what? We are going to react it with the your Felling's test. Okay, Felling's solution. What I am going to get? I am going to get the reddish brown PPT. Okay, so reddish brown PPT, and your aldehydes, they are oxidized to carboxylate ion. Okay, carboxylate ion. Okay, so this is the test. Oh, this is the test. So reddish brown PPT. So the color of the Felling's test is blue only. So if it shows blue, it is negative. Okay, there is no test. Okay, and if it turns like this reddish brown, that means that it is a aldehyde. So it is giving you a positive test for your Felling solution. Okay, this is a positive test for the Felling's test. Okay, solution. So so here when we are talking about the aldehydes, okay, so your only aliphatic aldehydes will show the Felling's test. Okay, aliphatic. Okay, not the aromatic. Only aliphatic aldehydes will show this Felling's test. Okay, and the Tollens test. Okay, Tollens test, the silver mirror test, and your Felling's test. So both these tests. Okay, these are the tests which are used for the distinguishing your aldehydes and ketones. Suppose I have a either I have a aldehyde or a ketone, I don't know. Okay, but I want to check, so I can use this method. Okay, if it is aldehyde, then both Tollens and Fellings will give positive. Okay, if it is a ketone, we are not going to get the test. It will be a negative test. Okay, so like this. So both these tests are the distinguishing test. Okay, between the aldehydes and ketones. Very, very important. So you have to remember the formula. You have to remember the color. Okay, positive test, what it will give, what is the formula, what is it consist of, okay, what is Fehling solution made up of, what is solid solution made up of. Yes, next is haloform test. Next is what? Haloform test. Okay. So haloform test, aldehydes and ketones. Okay. At least they should have one methyl group. Okay. At least one methyl group should be attached to the carbonyl carbon. Okay. So when at least one methyl group is attached to the carbonyl carbon, then okay, such are called as a methyl ketones. Okay. Then we are going to use sodium hypohalate. Okay, that is NaOX. So we are oxidizing it with the help of your sodium hypohalate. Okay, and it will give you corresponding sodium salts. Okay, with the of the carboxylic acid, which is having one carbon atom less than the carbonyl compound. So here, what we are doing, we are converting the methyl group to haloform. We can use either chloroform, bromoform, or iodoform. Okay, this is formed. Then this oxidation does not affect the carbon-carbon double bond if present in the molecule. So, okay, so then only this test is positive. So exceptional is ethanol. So here what we are going to take? We are going to take a methyl ketone. Okay, we are going to react it with sodium salt of carboxylic acid. Okay, sodium salt of carboxylic acid. What I am going to get? What I am going to get? We are going to react it with sodium hypohalate. Sorry, I'm going to react it with sodium hypohalate. I'm going to get the sodium salt of carboxylic acid and haloform. Okay, if it is X, can be your Cl, Br, and R, I. Okay, iodoform, bromoform, or chloroform is formed. So the positive test, it is answered. Okay, if you get a dark brownish type color, reddish brown color. Okay, so that means it is a positive test. So this is a haloform test. Okay, haloform tests are best answered by the aldehydes and ketone, which is having a methyl ketone. Okay, methyl group. If there is a methyl group linked to the carbonyl carbon, then only the haloform test is answered. Okay, by such aldehydes or ketones. Is it clear? Yes. So some of the examples of holoform test. Okay, so these are the compounds which will show you the positive test. Okay, only the exceptional is ethanol. Ethanol will not give you haloform test. Okay, so ethanol and methanol. So ethanol will give you. So methanol, there is no. So here you can see. Okay, so here there is a positive. Okay, only ethanol. Okay, your ethanol is having a methyl ketone, so positive. Here there is no methyl ketone. Okay, then your positive test. Okay, this is negative. Here again positive. Okay, here there is negative. Okay, so there is no methyl ketone. So similarly, so these are the different examples of the haloform test. Okay, just go through. Yes. Okay. Next is reactions. Okay, due to the presence of alpha hydrogen. Now, what do you mean by alpha hydrogen, students? Okay. So suppose I have a carbon like this. Okay, and carbonyl carbon. So the carbon next to the carbonyl carbon, it is alpha. This is beta, gamma, and delta. Okay. So like this. So these are the like this we name it. So aldehydes and or ketones having at least one alpha hydrogen. Alpha hydrogen means what? The hydrogen linked to the carbon, okay, just beside the carbonyl carbon. So at least one alpha hydrogen should be there. So if there is only alpha hydrogen, okay, to the aldehydes or ketone, at least one is there, then it will show aldol condensation. And this aldol condensation, it occurs in the presence of dilute alkali. You can use the dilute alkali like your NaOH, okay, sodium carbonate, okay, so barium hydroxide. So these are the different various dilute alkali which we can use for the aldol condensation. So there are two types of aldol condensation. One is the simple, or you can call it as a self aldol condensation. Self means the aldol condensation takes place between the similar or the same molecule. Okay, so it can be the similar two molecules. So aldol condensation, and another is the cross aldol condensation. Okay, so let us see. So this is the aldol condensation. So what is happening here in aldol condensation? So aldehydes and ketones. So very, very important aldol condensation. Okay, aldol condensation is very, very important. Please mark this also is very, very important. Okay, very, 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 very important. So aldol condensation, aldehydes and ketones, they should have, what is the necessity condition? They should have at least one alpha hydrogen. Okay, at least one alpha hydrogen. Okay, so then it will undergo self-condensation. And how it will go? In the presence of dilute alkali. So there should be a presence of dilute alkali. Okay, and what it forms? It forms a beta hydroxyaldehyde. It forms a beta hydroxyaldehyde, or if it is a ketone, it is formed beta hydroxy ketone. So if it is aldehyde, it is called as aldol. If it is a ketone, we call it as ketol. Okay, and this reaction, it is called as the aldol condensation. What it is called as? Aldol condensation. So suppose I have a acetaldehyde. Simplest I will take acetaldehyde plus acetaldehyde. So CH2H, okay, then C double bond OH. So you can see here, your if I tell this as alpha, okay, sorry, this is as carbonyl carbon, then this is a alpha carbon, and this is a at least one hydrogen is present. So what will happen? So your base, okay, in the presence of base, so base will abstract the proton. So there will be formation of the carbon anion. Okay, there will be formation of carbon anion minus CH2C double bond OH. So this will attack the carbonyl carbon. Okay, and this will get polarized. What I am going to get? I am going to get CH3, COH, H, CH2, C double bond OH. So this is our, so this is alpha, beta. So beta hydroxy. So beta hydroxy, okay, aldehyde, beta hydroxy aldehyde. Okay, or 1, 2, 3. So 3 hydroxy butanol. Okay, so further what will happen? There will be loss of water molecule. So water molecule will be lost, okay, like this. And what I'm going to get? A CH3, CH double bond, CH, C double bond, OH. So I'm going to get a it is a enal system. Okay, enal, but 2 enal. Okay, but 2 enal. So 2 in. So 1, 2, 3 and so 1, 2. Okay, 1, 2, 3 and 4. Okay, so like this. So the carbonyl carbon should get the least number. Okay, so I'm going to get the butanol system. Understood? Okay, yes. Okay, so this is the aldol condensation. I hope you have got it. So aldol condensation, what will happen? The base will abstract the proton from the alpha carbon, and there's a carbon anion is formed. You can see this is a base will abstract this proton, and the carbon anion is formed. This carbon anion, what will do? It will attack the carbonyl carbon of the other aldehyde, and what will form? A beta hydroxyaldehyde is formed. This beta hydroxyaldehyde will further undergo loss of water molecule when you heat it. And what will happen? You are going to get alpha beta unsaturated aldehyde. Okay. So this is about the self aldol condensation. Then we are going to see, so this is one of the example. You can see again one example. So they have taken what I have taken, that is with acetaldehyde. So you can see what is happening here. So base, okay, I'll show you. So what has happened? So the base will abstract the proton. Okay. So in turn, carbon anion generated. This will attack the carbonyl carbon. It will polarize. So I'm going to get CH3COH, CH3CH2, C double bond O. I'm going to get a beta hydroxyketol. This beta hydroxyketol, when you heat, water will be lost and a double bond is formed. Okay, so it is a alpha beta unsaturated ketone formation. Yes. Next is cross aldol condensation. So cross aldol condensation is between the two different aldehydes or two different ketones. Okay. So aldol condensation, it takes place between two aldehydes or two different ketones. Okay. Or it can be between aldehyde and one ketone. So it is called as a cross-aldyl condensation. Okay. So let me see. So this is about simple. Okay, here there is simple. So let me give you a cross-aldol condensation. So here are two. Okay, so this one is your this is your acetone. Okay, this is your acetone, and this is your uh, uh, propinaldehyde. Okay, this is your propinaldehyde. What will happen again? Propinaldehyde. So it will abstract the proton. Okay, it will abstract the proton from the alpha carbon. Okay, and this in turn will attack the carbonyl carbon, and you're going to get what? Your beta hydroxy. Okay, I'm going to get a beta hydroxy aldehyde. So this beta hydroxy aldehyde, what I'm going to get further? So further, when you heat it, so the water, okay, I'm going to get C double bond C. Okay, so I'm going to get alpha beta unsaturated aldehyde here. So similarly, okay, so like this. So in case of cross aldol condensation, any one aldehyde or ketone has alpha hydrogen and does not have alpha carbon, then also reaction is possible as given below. Okay, so here also you can see. Okay, so cross aldol condensation takes place. Understood? So cross aldol, and what do you mean by self condensation? Yes, yes, students. Okay, okay, fine. Let us go further. So next is the Carin-Zaro reaction. Okay, next is the Carin-Zaro reaction. So Carin-Zaro reaction, aldehydes which do not have any alpha hydrogen, okay, such as formaldehyde, okay, or benzaldehyde, okay, undergo self oxidation and self reduction on treatment with concentrated alkali. Okay, so here one molecule is reduced to alcohol and another molecule gets oxidized to salt of carboxylic acid. So let us see the example. So Carin-Zaro reaction, it is when you do not have any alpha hydrogen atom. So the it is done on the aldehydes which does not have a alpha hydrogen atom. Now I hope you know what is alpha hydrogen atom. Okay, so here you can see, where is alpha hydrogen atom? No, there is no such alpha hydrogen atom here. Okay, because alpha hydrogen means what? Like, beside the carbon, there should be a carbon. To that carbon, alpha hydrogen should be there. Okay, so there is no any alpha hydrogen. So it is taking place in the presence of an alkali. So what you are going to get? One will be your alcohol. Okay, so it is reduced to alcohol, and another is the salt of carboxylic acid. Okay. So I'm going to take two molecules of your formaldehyde, react it with sodium hydroxide, or you can take potassium hydroxide, followed by you have to heat it. I'm going to get what? I'm going to get a methanol here, and I've got a sodium salt of your carboxylic acid. Okay. Similarly, so your I can get what? I can get your Na. So it or it is a potassium formate, right? This is a potassium formate. If I use potassium hydroxide, this is a potassium formate. This is methanol. Okay. Now suppose I have taken benzaldehyde. Suppose I have taken here benzaldehyde. Now benzaldehyde reacted with arginine benzaldehyde in the presence of KOH. Okay, heat it. What I'm going to get? One will be a benzyl alcohol. Okay, one will be a benzyl alcohol. Another is your sodium benzoate. Okay, sodium benzoate. So what will happen here? So one will be CH2OH. Okay, and another will be COONA, like this. Okay, so I'm going to get the reaction. So what is happening here? We are treating it with a strong alkali. So oxidation takes place. Okay, oxidation takes place. Understood? So your oxygen is added. Okay, oxygens are added here. Hydrogen is removed. Okay. Next is electrophilic substitution reaction. So electrophilic substitution reactions, aldehydes, that is the aromatic aldehydes and ketones, they undergo electrophilic substitution reaction. Okay, add the ring, the carbon. Okay, the ring carbon, the carbonyl group. So you see that the carbonyl group, it is the electron withdrawing group. Okay, and what it will do, it will deactivate. Okay, it will deactivate the benzene ring. Okay, and thus it is a meta-directing. Okay, it is a meta-directing because electron density decreases on ortho and para position. Okay, so it is a meta-directing group. So let us see the halogenation. So formal benzaldehyde in the presence of Cl2 and FeCl3. Okay, I'm going to get a compound. Okay, that is your metachlorobenzaldehyde. Okay, so plus HCl. Similarly, okay, so this, okay, so you're going to get whatever the incoming electrophile is there, that is going to attack the meta position. Okay, yes. Then next is nitration. So for nitration, we are using concentrated HNO3 and concentrated H2SO4 as a nitrating mixture. So what is the nitrating that is a electrophile? It is nitronium ion. So nitronium ion, the incoming nucleophile electrophile will attack the meta position. Sulfonation, we are making use of fuming H2SO4, SO3H. Okay, so it is again the ortho position, meta position. Okay. Yes. So what are the uses of aldehydes and ketones? So 40% of formaldehyde is known as formalin, used in preservative of biological specimens. So you might have seen in biological lab, there are different specimens. Okay. So these specimens, how they are still like that only. Okay. So because you are using the formalin. Okay. Because you are using formalin, the biological specimens are as it is. Okay. They do not get spoiled or you don't get any bad smell. Okay. So formaldehyde is also used as disinfectant. So it is used as disinfectant. Acetaldehyde. Okay. Acetaldehyde is used for silvering the mirrors. Then benzaldehyde is used in perfume industries. Acetone is used as a solvent in industries. Okay. It is used as a solvent in industries. Then acetone, it is used as a solvent in industries as well as paints, okay, or as well as for paints. Then many aldehydes and ketones like your vanillin, okay, cinnamaldehyde, okay, used for the flavor. So vanillin, it is used as a vanilla flavor. Cinnamaldehyde is used as a cinnamon flavor, and so on. Okay, so these are some of the reactions and the physical and chemical properties about the uh, ketones and aldehydes. Okay, so next is we are going to see about carboxylic acid. So we are left with a very small part. There is a carboxylic acid. So just a second. So I'll share the other PPT. Yes. So we have completed about aldehydes and ketones. So now we are going to see about the carboxylic acid. Okay, now we are going to see about carboxylic acid. So let us start about carboxylic acid. Okay, so what are carboxylic acid? Already we have discussed. Okay, so carbon compounds which contains a carboxyl group and the functional group COOH is called as the carboxylic acid. So this carboxyl group consists of a carbonyl group which is attached to the hydroxy group, right? So your carbox, so this is your carbonyl group which is attached to OH. So this is your carboxyl. It is called as a carboxyl. So this carboxylic acids, they are of two types. One is the aliphatic and there is the aromatic. Okay, aliphatic means what? Alkyl groups. Okay, there is alkyl group. Suppose they are attached to a COOH group. And what do you mean by aromatic group? So there is a benzene ring. Okay, to this benzene ring, what is present? So to this benzene ring, your this is present. What? to your benzene ring, your what you say, the your carboxylic group is present. Okay, so large number of carboxylic acid, they are found in nature. Okay, but some higher members of aliphatic carboxylic acid, they are known as the fatty acid. They are known as what? Fatty acid. So remember that. So carboxylic acid, what is a functional group? Okay, how they are divided? They are divided into aliphatic and aromatic. And aliphatic, the alkyl group is attached to the COH group. In aromatic, the aromatic ring is attached to the COH group. Okay. Then, so this is about the carboxylic acid. Next, we are going to see the nomenclature, how to name the compounds of the carboxylic acid. So, large number of carboxylic acids, they are known by their common names. Okay. And many of these are the naturally occurring. The common names, they end with the suffix. What do you mean by suffix? Suffix is the ending name. Okay. So the ending name is ic acid. The ending name is ic acid, and they have derived from the Latin or Greek names, okay, of their natural sources. So formic acid, okay, it is first obtained from red ants. Okay, red ants. So formic acid is obtained from red ants. Then acetic acid, it is obtained from vinegar. Okay, butyric acid, it is obtained from rancid butter. Okay, rancid butter, in that butyric acid is present. Now we will see the IUPAC nomenclature. So that was about the your common name system. This is IUPAC. So aliphatic carboxylic acid are named by replacing the end in the ENE. So suppose it is methane. Okay, suppose it is methane. So what I'm going to do, I'm replace this E with oic acid. So I'm going to replace it by methonic acid. So like this. Okay, so my name E will be replaced by OIC, oic acid. So this is about the IUPAC system. So presence of one carboxylic acid is oic acid. If you have two carboxylic group, you are going to say dicarboxylic acid. If there are three carboxylic acid, I'm going to say as tricarboxylic acid. What I'm going to say? Tricarboxylic acid. So now how you have to give the priority? So functional group, okay, present along with COH group, then that group gets lesser priority and can be used as a prefix of that group. So any other functional group, okay, along with your COH group, it will be given the lesser priority and it will be used as prefix. Prefix means you have to write the whatever the this is there, that the name, okay, that you have to write before, and then you have to end it with the suffix of oic acid. And only sulfonic acid has higher priority than that of the COH group and can be used as suffix. Okay. So these are some of the namings. So let us see. So here when you are naming, so first I'm going to name this. So 1 and 2. So it will be 2-methyl again, but I have to follow the substitution first. So 2-methyl. Okay. So 1, 2, 3, 4, 5. So it is 2-methyl cyclopentane carboxylic acid. Okay. Then again, so this we should get the least number. So 1, 2, 3. So it is what? 3-phenyl. Okay. Then 1, 2, 3 is propanoic acid. Then this is benzoic acid. This is what? Benzene 1, 2 dicarboxylic acid. Because there are two COH group, we call it as dicarboxylic, and we have to mention the positions of both the carboxylic acid. So 1 and 2 position has to be mentioned. Okay. Yes. Okay. Next. So next compound. So here you can see. Okay. So 1 and 2 position. So COH will give the first name. So I'm going to get, so this will be a substituent. So 2-hydroxy benzoic acid. So similarly, so the common name is salicylic acid. Then here again 1, 2, 3, 4. So 4-methoxy benzoic acid. Okay. Then we are seeing diabasic acid. So 1, 2. So it is a ethane dioic acid. Okay, 2 carbons, so ethane dioic acid and oxalic acid. So, and this is what? Malonic acid is the common name, and it is propane, 1, 2, 3, propane dionic acid. Okay, so these are the names of the your carboxylic acid. So similarly, few more. So you can see the number of carbon atoms are 1, 2, 3, 4. So it is butane dioic acid. The name is succinic acid, common name. And this is 1, 2, 3, 4, 5. So this is hexane dioic acid. Okay, hexane dioic acid. Then it is a glutaric acid. It is what? It is a glutaric acid. Okay. It is not hexane. Okay, there are 5, no? So it is pentane. Okay, it is pentane dioic acid. Okay, it is pentane dioic acid because there are 5 carbons. Okay, when you have 1, it is meth. When you have 2, it is eth. When you have 3, it is prop. When you have 4, it is but. When you have 5, it is pent. When you have 6, it is hex. When you have 7, it is hept. When you have 8, it is oct. When you have 9, it is nonan. And 10 is decan. Okay, so remember this. Okay, yes. So there are 5 carbons. So we are going to name it as pentadioic acid. Dioic means because 2 these are there. Okay, now let us see the structure of carboxylic acid. So let us see the structure of carboxylic acid. So you can see the structure of carboxylic acid. Here the carbonyl carbon. Okay, because you are having a double bond, so it is a sp2 hybridization. Okay, so whenever you have a double bond associated, then the carbon is sp2 hybridization. If it is a single bond, it is a sp3. Okay, if it is a triple bond, it is what? It is a sp. Okay, so this is a sp2 hybridization. So the carbonyl carbon is sp2 hybridization. It is a planar. Okay, it is planar and the bond angle is 120 degree. Okay, it is a 120 degree. Okay, so here the carboxyl carbon it is less electrophilic. Okay, than the carbonyl carbon. Okay, so here you can see. So this oxygen is sp3 hybridization. This is sp2 because it is associated with double bond. This is also sp2 and the bond angle is 120. So you can see the resonating structure. When you see the resonating structure, you can see that the carboxylic carbon, okay, it is less electrophilic than the carbonyl carbon. Okay, because as you can see the resonating structures. Okay, because you can see through the resonating structures how it is. You can find it out. Okay. Yes. So let us see the methods of preparation of carboxylic acid. First one is from primary alcohols and aldehydes. Okay. So from primary alcohols and aldehydes, so we can convert the primary alcohols to carboxylic acid. So primary alcohols are converted to carboxylic acid. We can use potassium hydroxide. Okay. That is your potassium permanganate. Potassium permanganate, we can use it as in neutral medium. It can be used in acidic medium. Okay, or it can be used in basic medium. Okay, or also you can use the potassium dichromate. Okay, in the presence of your sulfuric acid, or you can use the chromic acid. Okay, in the presence of H2SO4, which is called as a Jones reagent, which is called as a Jones reagent. So what we are using, we are doing conversion of the primary alcohol. We can use any this alkaline KMNO4 I can take, okay, followed by acid hydrolysis. What I'm going to get, I'm going to convert it into corresponding carboxylic acid. Okay, so let me take one example. So if I take CH3, CH2, 8 times, CH2OA. So what is the name? So this is 1, 8, 9, 10. Okay, 8 and 1. So it is 8, 9, 10. So 10. So it is decane 1 all. Okay, so decane 1 all in the presence of chromic acid and H2SO4. What I'm going to get? I'm going to get CH3, CH2, 8, CH, COH. Okay, so this is the answer. So I'm going to get decanoic acid. Decanoic acid. Okay, so this is the answer. So like this, we are going to do the oxidation. So primary alcohols, okay, and aldehydes. So primary alcohols are oxidized to carboxylic acid. Okay, you can use the following this. Okay, alcohols are converted to carboxylic acid. Yes. Then next is from alkyl benzenes. Next is from alkyl benzenes. The aromatic carboxylic acids, they can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic or alkaline potassium permanganate. So here the entire side chain is oxidized to carboxyl group irrespective of the length. Okay, so let us see. So toluene is taken. So toluene is taken. What we are doing? We are treating it with your potassium permanganate, okay, in the basic medium, that is your potassium hydroxide. We are going to heat it. I'm going to get a potassium benzoate. Okay, I'm going to get a potassium benzoate. This potassium benzoate, further, I'm going to do acid hydrolysis to give you benzoic acid. I'm going to get benzoic acid. So what is done? Side chain oxidation is done. So entire side chain is oxidized to carboxylic group. You can see CH3 is oxidized to COH. Okay, so your primary and secondary alkyl groups are oxidized. Okay, but tertiary alkyl oxide, tertiary group is not affected. Okay, we cannot do any oxidization on tertiary group. Okay, so primary and secondary group alkyl groups you can do. So again, similarly, one more example. So this is the propyl group. So it is N-propyl benzene. So we have taken N-propyl benzene. We are treating it with KMnO4 in the presence of potassium hydroxide heated. I'm going to get a potassium benzoate. Okay, I'm going to get a potassium benzoate. This potassium benzoate followed by acid hydrolysis. I'm going to get a benzoic acid. I'm going to get what? Benzoic acid. Understood? Okay. So another name reaction. Is it clear? Yes. So in today's class, what all things we have discussed? Yes. So what all things we have discussed? We have discussed about the uh, uh, reduction methods. Okay, reductions. Okay, so we have discussed about the reduction. So reductions to alcohols, your aldehydes or ketones. Okay, they are reduced to the alcohols. Okay, then reductions to hydrocarbon. So both the aldehydes and ketones, they can be reduced to hydrocarbons, which are the name reaction, Clemenson's reduction and the Wolff-Kishner reduction. Okay, then we have seen the main important reaction, that is Tollens test and Felling's test. Okay, then also we have seen the haloform test, very important haloform test. Okay, in haloform test we are using what? Sodium hypohalite. Okay, yes, and what is the necessity condition? That there should be a methyl ketone. Next, we have seen aldol condensation. So self-aldol condensation and cross-aldol condensation. Okay, then we have seen Carin-Zaro reaction. Then we have seen electrophilic substitution reaction. Okay, then we have started with the carboxylic acid. So carboxylic acids. Okay, we have seen nomenclature. We have seen the structure. Okay, and two methods of preparation of carboxylic acid. Okay, so the remaining things of carboxylic acid, so we shall be discussing in the tomorrow's class. Okay, any doubts up to here? Yes, is it clear? Any doubts? Okay, fine. So I shall end this session here. So we'll meet in the next class. Thank you.